So this is nice to know stuff. So this won't really be on a test. This is called the left-hand rule of conductor flow. So uh, magnetic fields rotates around the conductor, right? Didn't I show you my electromagnet the other night? In fact, I got another one over here. This is not very efficient, uh, but you can generate or figure out which way the North Pole and the South Pole is, and they have one for motors also too. But this is for electron flow. So basically, this is the only thing different when you teach. We have two methods of teaching current flow. We have what they call conventional current flow, and then we have electron flow. We teach electron flow here. Uh, our books covers electron flow. Conventional current flow teaches that current flows from positive to negative. In electron flow, we teach that current flows from negative to positive. Does it make any difference in any of the math? No, it don't make any difference in the math. It don't make any difference in almost none of the rules. The only thing it makes a difference is when you figure out figure out what's the north and the south pole on the current flow. So here they call it the what? They call it the left-hand rule, right? Okay, they call it the left-hand rule for this is electron rule. Well, if it was conventional current flow, it would be what? The right-hand rule. That's the only difference. So just the only thing that changes is the rules for electromagnets. Everything else is exactly the same. When you in DC, when you put up the polarity on your resistors, you mark the polarity. That has nothing to do which way current flows. All your math has nothing to do which way current flows. Your math has no difference on which way you connect your meter up, right? You understand? And on AC, this only applies to DC anyway, because AC, what's happening? Yeah, so this guy right here, swapping polarities 120 times a second, because it's 60 cycles. 60 cycles is made up of one positive alternation and one negative alternation. So that would be, it actually swaps direction 120 times a second. So, that's not very much. That's 8.33323 milliseconds that it swaps directions. If y'all don't know engineer notation yet, it's 0.003 .0083333 seconds. So normally we consider AC not to have a polarity because it constantly swaps, but normally we still make one of our leads what we call a common, right? You understand? And one of our leads we refer to as the active lead or the hot lead, or whatever you want to call it. So the problem we have with DC, so AC is self-extinguishing, so it's hard to maintain an AC arc. I'm not saying you can't. If it gets close enough, it will. But AC is self-extinguishing because it goes to zero 120 times a second. DC does not. So DC contacts, high-powered DC contacts, they had to come up with a method where they could literally blow the arc out. So big DC contactors have what we call a blowout coil. So we have the current flowing through the blowout coil. So this is actually the current flowing out to the motor. So this thing, when the motor's running, it builds up a big magnetic field, and it might put out a north on this side, and it might put up a south on that side. It builds up, magnetic field comes out, and then when you turn that motor, when you turn that contactor off, that magnetic field collapses. And when it collapses, it flows through the arc, and it literally blows the arc out. So these are called blowout coils. You won't run into them on AC contactors. You'll run into them on big DC contactors. We had 5-speed DC cranes out at U.S. Steel, and so that we had these things out there, and we had one of the blowouts actually fall off, and it fell down onto the side. and that contact was just, and the motor was trying to run all the time, you know. So how did we extinguish the arc? We blew it out. So we blew it out. So one of the blowout coils, and then of course we fixed it. So you're only going to run on blowout coils for DC contacts. We had a big DC panel. I don't know what happened to it, that had a bunch of big power DC relays. We used to have a lot of DC motors. And what advantage does a DC motor have over an AC motor? Yeah, control. I mean, we control. If we increase the field, the motor slows down, but it creates more torque. And if we increase the current going to the armature, the motor speeds up. So we can, not only can we control the speed, but we can also control the torque of a DC motor. And they did that out at U.S. Steel. They had they were sensing the torque all the time. And to keep it running at the same speed, they'd increase this a little bit and increase that a little bit, and the motor would run basically at different torques if they needed it. So that's the big advantage of DC. AC, though, is a lot cheaper because DC, we have to provide current to the rotor rotational portion, while AC, we induce it in there. So DC motors or AC motors are a lot cheaper per horsepower. But once they came up with those variable speed AC drives, they're still not as good, but they want to create a constant torque. But AC motors are so much cheaper. So now AC motors are dominating your speed control circuits because of the cost. The cost of the electronic drive is about the same. So where do they save their money? Oh, they save them on those AC motors. So most of our cranes out of U.S. Steel were DC when I worked out there because they could control the speed a lot better. But this was before variable frequency drives. We call them variable frequency drives. I call them variable speed drives because if you just vary the frequency, it wouldn't work. You have to vary the frequency and the voltage to make the motors work. So this is in fact, this looks like the panel we had here. So you can literally see the blowout, the actual arms right here that would come up and would actually blow out the contact. This looks like the panel we had here. Sure does. So it's probably got thrown away. NEMA ratings for contact standard, they're usually rated for sizes depending on the amount of current they can handle. Okay. This is horsepower, NEMA rating for horsepower. So a size 0 could run a 1.5 horsepower motor on 200 volts. It could run a 1.5 on 230. It could run a 2 horsepower on 230 or 460. And it could run a 1/3 horsepower on, and so if we look at this motor, where's our motor starter at? And this is going to be on the nameplate on the motor starter, its actual size. So that big one that I pulled out, that was a size 3. So size 0. So this right here is a size 00. So we'd have to, this is not even in that chart. Yeah, as soon as it focuses in, hold on a second. You'll see it right here. So here's NEMA size 00. So this guy right here, we would have to look that up. We don't even, that's not even rated. But our 3-phase motor is only a, I think it's a 3rd. Yeah, our 3-phase motor is only a 3-phase, it's a 1/2 horsepower. So we'd have to actually look this one up on a different chart. So you can imagine if that's a 1/2 horsepower AC motor, couldn't you imagine like a 600 horsepower AC motor? Huge. So size ratings. This is a table. Yeah, this is right off NEMA. You can actually, you don't need to see this, but they're rated in sizes. Of course, the bigger the size, the bigger they can run. So size 9 could run at 230. It could run a 800 horsepower motor. At 460, it could run up to 1600, right? Uh-huh. So why can it run such a bigger size motor? Because it's at a higher watt, a higher voltage, right? The bottom one makes more sense, but it don't show that. Yeah, that is 00. I'm sorry. So ours is rated at one third horsepower. Thank you. I didn't even see that. So ours motor is a 1/3 horsepower. We're running on 208. We're running ours on 208. So we're basically not even taxing that thing, and we're running our motor unloaded. So that means it's not developing this horsepower at all, right? You understand? So are we okay? Contactor dimensions vary from inches to several feet in length. A magnetic motor starter is a contactor with overload protection, so we already know that, right? So we have three sizes. We have contactors. They're designed to operate in the power circuit, right? But they have no overloads. A magnetic motor starter is basically a contactor with overloads. And like I said, usually you can buy the contactor separate. So normally what the company does is they'll have a metal plate and they'll mount the contactor on it, and then they'll mount the overload on it, and then they'll wire that contact in there. So that little short wire that we see, you don't access that. That's done when they add that overload. So we see when we wire this up, when we do our wire numbers, wire 9. So let me bring my camera back up. See if we can see the actual wiring. Oops. Wrong way, Rich. Here we go. Yeah, I'll get it in a minute. So here's the actual wiring right here. And that's what's nice about these on the black. They actually show you the wiring. So the overload is right. Let me see. Well, it's on my side. The overload is right here. So we're going to wire it to 9. They don't show a wire. They don't show a terminal here because that's internal. So we'll wire between 10 and 9 would be where our coil's at. Or you can use 3, but it's also connected to a contact, so we usually don't use that one. And I'll show you why they did that, but we very seldom use it. So this was done. This is not normal right here. This jumper they have right here between 10 and 3. So why they did that, I don't know. We are to break it. So like I said, it's up to you which one you want to use. If you want to use the one with the electronic overload on it, that's fine. But you'll have to get the manual. They're usually in the blue tables inside the drawers right there. That shows you how they're wired, or you can use these. And I think we have plenty of these by the guy. Most of the time we're going to start out using one, but when we get to the reversing circuit, we're not going to use a true reverser, and we'll show y'all one of those. We'll just use 2 of these to reverse it. And there's more back there on the shelf if you need them. So what time is it? Okay, we're okay. So contactors with overloads. So a lot of this is just repeated stuff, guys. Magnetic overload relays used a current control switch at a specific overcurrent. So we have magnetic overloads too. Those are going to be sealed up. So what they're doing is they're using an electromagnet to actually actuate the overload or trip the overload. So it acts like a solenoid. You're okay on solenoids, right? I got one around here if you want me to show you that again. It's a DC solenoid. So how can we tell if a solenoid is AC or DC, or a relay is AC or DC? So if you put an if you got a 120 volt AC coil and you put it on 120 volts DC, you're going to flat burn it up and blow fuses and stuff like that. So in electronics, in AC, most of your opposition on a coil is given, and y'all don't need to know this, it's given by this formula here, 2 pi FL. And this is a given, so normally we just use 6.28. And then the frequency would be what frequency you apply to it. So Alabama Power would be 60 hertz. And then L would be basically how many loops you have in a coil. It's called the inductance. So what happens if frequency goes up? Well, the opposition to the coil, so this is opposition, by the way, and it's given in ohms. So all opposition to electric flow is in ohms. We call this reactance because it reacts to frequency. DC don't care. And resistors don't care. Resistors don't care. If you put 100 volts DC or 100 volts AC on a resistor, it don't care. When you put it on a coil, it does care because now the opposition is going to vary with frequency. So it's depending on frequency. So if I come over here and make this 0, what does X of L go to? X of L goes 0. Of course, it don't because it's got the resistance of the wire, so you're going to burn stuff up. So it's depending on that 60 cycles to get the opposition it needs to work. So that means AC relays are going to have fewer coils. DC is going to have hundreds of coils because the only thing it gets its opposition from is the resistance. The only thing it limits the current on a DC relay is the resistance of the wire. AC relays has X of L that it deals with, so it's going to have less. It's going to have less turns of coils. So don't put an AC relay on a DC, right? You can the contacts, but not the coils. Everybody understand that? Okay. Plus, it's going to have AC relays are going to have laminated cores, right? You understand? We talked about that. What does that do? Well, it limits the current that's induced into the core that's trying to concentrate the field. So as soon as you see that lamination, you know it's dealing with some type of AC. So you can identify them real easy. And normally, this is after. Normally it'll be labeled on the actual coil, but sometimes that gets wore off, guys. Believe that or not. So bimetallic strip. So bimetallic strip. What way this works, and I don't have one around here, but a bimetallic strip, basically it has two metals that are mechanically joined. So they're actually joined together. And each metal has what we call a different, y'all know metals expand when they get hot and they contract, but does all metals expand and contract at the same time? Say no. No. So we have two metals that have what we call different coefficients of expansion. So let's say this one down here expands faster than this one right here. Well, what's going to happen, it's going to cause this thing, when it heats up, it's going to cause it to do what? It's going to cause it to bend, it's going to warp. And so this is the way these overloads work. This is technically the way your circuit breaker works in your house. It runs the core, it runs it through a bimetallic strip of metal. It's got a little bit of resistance to it. As heat goes, as current goes through it, it heats up. When it gets up to a certain temperature, it pops off a little edge and trips. And this is why most circuit breakers, if you're there when they pop, you can't do what? You can't reset them. You got to let them what? Yeah, in houses. They do have all types of circuit breakers, by the way, but most of our houses use the ones with the bimetallic strip in there. So we can use that for overloads. In fact, they're showing it here, actually warp. So they got a spring. The bimetallic strip is holding it up, right? You understand. Current flows to the bimetallic strip. When it gets up to a certain temperature, it pops and opens the contact. A very simple circuit. And then once it cools down, we can do what? We usually can reset it. So bimetallic strips. Trip indicators indicate that an overload has occurred. So normally these things, some of your solid state, they'll actually have LEDs. what ours has, the ones that we have, as soon as I stop going past mine. So the one we have right here, it's got this little window right here. And this thing's not going to pop up when it trips. This right here will turn red. Indicates that thing's flipped over, right? Understand? Which means it's tripped. So usually there's a trip indicator for your overloads. I put my other one away. So it's got some type of indicator that you can look at real easy and tell it's what? It's tripped. Standard overload relays may be used on very large starters by using current transformers with specific reduction ratios. So a current transformer, y'all understand that? So what do we mean by a current transformer? Well, no, usually don't step it up or step it down. What we do is we take a bunch of coils of wire, and then we come over here and we take our conductor and we run it through it. And this would be called a current transformer. Now, the EMF we get off this thing, or the volts we got out of it, would be directly proportional to what? Current. What determines the amount of current we get by induction? Right? So it would be what? It would be what? It would be, first of all, we got to have a magnetic field, right? And what do we get? What do we get when we put current through a conductor? We get a magnetic field, right? Then we got to have a what? We got to have a conductor. And then we got to have motion. What determines the amount? Well, let's go right down the line. Strength of the field. So the more current we put through that thing, the stronger the electromagnetic is, right? Right? You understand? And this is what that's and then we got to have the number of conductor loops. So the thing's going to have a bunch of loops. And then we got to have motion. Well, motion, AC gives us motion, right? You understand? So that means how much voltage I get off that coil right there would be directly proportional to the amount of current. If it's directly proportional to the amount of current, then I can use that to trip an overload. We call these CTs. We had them all over the place at US Steel. We'd have a little old tiny ammeter up there on a control panel that was looking at 300 or 400 amps. Well, what they did is they had a little CT current transformer around that, and they run the output of the current transformer up to the ammeter, right? You understand? So we use these CTs all over the place to sense current. That's the way a clamp-on ammeter works. So a clamp-on ammeter uses a current transformer, right? We call them CTs. But all it is doing what? It's measuring the strength of the magnetic field being created by the current. So anybody who tells you a clamp-on ammeter is an ammeter is not exactly true, right? It does what? It's measuring the strength of a magnetic field. So that means what's nice about a clamp-on ammeter is that we don't have to break the circuit. But normally they only work with what? AC. Yeah. So like I said, you can get them. We have a device. We have a solid state device called a Hall effect sensor that actually can give you an analog output that represents a DC current. So some clamp-on ammeters will measure DC current if it's got that Hall effect in there, but they cost quite a bit more than just a standard clamp-on ammeter. Standard overload relays may be used a very large starter by using a current transformer. A lot of people call them CTs, which specific reduction ratios. Okay, so over here we might have 500 amps, and then over here we might get 2 volts for 500 amps, and then it's up to whatever's taking that output voltage to determine what the actual current is supposed to be. The nameplate of a magnetic motor starter, we've already looked at that. Some of the things it's probably going to give us is probably going to give us the size, right? And then it'll come up here and it'll tell us at what voltage and what phase, what horsepower motor it can run. So notice as the voltage goes up, the horsepower goes up. Right? But you're going to have to y'all understand that? Right? Good. So this is the NEMA size chart. So this is, I don't know, there used to be a copy, a basic NEMA size in your textbook. I think there was one. But we already looked at this, right? Amp ratings. So size 0, the contacts are rated at about 9 amps. And that would give us all these different horsepower motors right here, depending on the watt. Yeah. So 9 amps. Well, we could run up a 2 horsepower motor with 9 amps, right? You understand that? But it would have to be what? Yeah, 3-phase. I forgot about that. Are we okay? With this motor starter. So we're down here. We're 230 or 208. So 1.5 horsepower motor, right? 3-phase. I'm sorry. We're 3-phase, but we're not even. We're not. Ours is what, a third of a horsepower, I said. So, well, we can't get them smaller than that. So motor nameplate. So how we are? So motor nameplate. What's one thing that's going? Y'all know what the motor nameplate is now, right? Everybody okay there? So that's going to be on the motor, and one of the things it's definitely going to tell us is what? The number of phases, right? Okay. Amps. So that amps rating is not your start current. What's the amps rating? Right, at the right voltage, developing the right horsepower, right? Okay. Then we have something called a service factor. What's the service factor? Yeah, so ours has a service factor of 1. What does that mean? It means you can't overload it, right? Can't overload it. So we definitely couldn't plug it. Y'all know what plugging a motor is? Plugging a motor is when you change directions without letting the motor come to a stop. So probably y'all plug y'all ceiling fans all the time, right? Anybody got a ceiling fan? Anybody reverse it? What does it do when you reverse it? You flip that little switch and so it's pulling quite a bit of current, right? Because it's pulling starting current basically, or a little more. So that's called plugging. So plugging a motor is when you do what? When you reverse it without it coming to a stop. Some motors are designed to be plugged. These are the motors that are going to have a real high service factor, like 1.5 or something like that. A motor that's got a service factor of 1, you need to let it do what? You need to let it stop, especially if it's under load. It don't really bother us if we plug these motors in. Why is that? Because the only thing they're going to do is the only inertia that it's got is the inertia of the rotor. So we're not running our motors under load. But don't reverse that. You might blow the fuses. So service factor, that's going to be on there somewhere. It's going to be labeled SF. Amps, it's not going to be the starting amps. That's going to be that's going to be the what? The running amps, if it's running its rated horsepower. So ours, if we put an ammeter on the thing and measured it, it says it's going to pull a certain amount of current at 208. Ours will be a lot less than that because we're not running at its rated horsepower, right? Manufacturing instructions on thermal overload. So this is about where we're going to stop. Well, so this is where you actually calculate your overloads. So we're not going to do that tonight. So I'm going to come up here and say where we need to start at. Trip indicators. So next time we go to lecture.